Hey folks, how's it going? This is Mr. Murray coming to you with a video on graphs of quadratics without any tricks. Okay, so in this video, I'm going to be talking to you about some kind of basics behind graphs of quadratics. All right, what they are, some important things to note, and kind of how to understand this as we transition into a new kind of realm of algebra where there's really not any straight lines at all anymore, right? You had some, at least like with piecewise and absolute value, everything about them was straight lines. There's no more straight lines anymore, but there is a lot of really cool, beautiful patterns and symmetry about these graphs that actually makes them a really cool unit to study. I think probably one of my favorites, if not my favorite unit of the year. Is quadratics. Okay, so what we have here is we're going to start by focusing on what we call standard form. Okay, now standard form of an equation that's linear, we saw that already. We've seen that. That's kind of like mx plus b. Now we're working with quadratics. Okay, and what makes quadratics special is that they now have a term that has an x squared with it, right? So we're technically supposed to say that a is not equal to, or rather not greater than, but a cannot be equal to 0, right? Because then otherwise it would just be bx plus c. Okay, so this is what makes quadratics stand out. Okay, the fact that they have this x squared term as part of them, in addition to, optionally an x term and a what we call constant term. That's what c really is. It's the constant term. Okay, so graphs of quadratics are called, and I think we might have talked about this, or you may have learned about this before. These are called parabolas. Okay, parabolas. Okay, some of us kind of say they look like U's or happy faces. Okay, or sad faces, and so they have a lot of nice features about them. The main one, and we'll talk about some other rules you might see along the way, is that they have this really beautiful symmetry about them. So if you could imagine taking this part of the graph and cutting it and folding this paper over, right? So we like cut it and we kind of fold it over. What you'll notice is you'll notice that it's perfectly symmetrical about this line, right? One will fold nicely on top of the other, all right? And that is because with quadratics, mostly having to do, or almost entirely, if not entirely, having to do with the squared term, right? Numbers, when you square them, there's not like a unique output. So for example, if I was to plug -1 into x squared, it would be the same thing as if I plug in 1, okay? And so what we're going to get is a lot of inputs that have the same output, all right? And we'll learn maybe more next year about the consequence of that. Okay, sorry about that. So anyway, we have some nice symmetry. We know that some of them point up and some of them point down, but we're not quite sure yet. We're not quite sure yet how we know this, and I'm not teaching tricks without tricks because I want you to kind of discover what's going on here, okay? And then once we have that understanding, then that's the point where we can make those notes and make that happen, okay? So here's my first graph for you, okay? X squared plus 6x plus 5. How do I graph this? Well, notice what I've given you here is really a table, right? Okay, that's my main slogan. You see it in class. Hopefully you've seen it all year on the board. Make a table, okay? If you ask me, where do I get started? I'm just going to say make a table because look, you have to be able to connect this table to the equation to the graph, okay? When I plug in numbers, x's, I get y's. So for example, when I plug in 0, I've got 0 squared, which is 0, plus, right, plus 6 times 0, plus 5. Okay, and what are these? This is 0, this is 0. So when I plug in 0, what comes out is 5. So the point 0, 4, 5 is on the graph of the equation. So that is the connection. If an input and an output make a function true, in other words, if this number, when I plug it in, gives me this number when it comes out, the point 0, 5 needs to be on the graph of the equation. That's the connection. The inputs and the outputs are the points on the graph of the equation. Okay, so a table simply lists those inputs and outputs, which we can convert into points and put them on the graph. Okay, now here's an example that doesn't work. 1, 5. I know right now, let's watch. When I plug in 1, what do I get? Well, look, I get 1 squared plus 6 times 1 plus 5. Okay, 1 plus 6 plus 5, that's 1, that's 7, that's 5, that's 12. Okay, so what does this mean? This is what I'd have here, but look, 1, 5 is not going to be a point on the graph because when I plug in 1, I don't get 5. I get 12. So that's the connection between inputs and outputs, the tables that list them, and the function itself. Okay, now I always say the good place to start is the y-intercept. Okay, if you can start there, that's great. Now, they're not always going to be on the graph, but it's an easy plug-in because when you plug in 0, this is always going to go away. You're always multiplying by 0. This will be what's left because 5 is the only number that doesn't depend on x. It's always going to be 5 no matter what you plug in for x. And if you plug in 0, right, that's all that's going to be left. Okay? All right, so the constant term is important. All right? Now, why did I plug in 1? Well, 1, look, you're making a graph. You need to plug in numbers. So if I'm you, what I would want to be doing is starting with the numbers that are easiest to plug in. Best case scenario, they're not on the graph, or worst case scenario, I suppose they're not on the graph. Best case scenario, they are. But you know what? Even when they're not on the graph, they can actually provide us a lot of information. Watch. So look, 112, that's way off the graph. So look, notice that as I'm going from left to right, the y's are going up, and this is already off the graph. Why would I plug in 2? I wouldn't, right? Because we can already see if I plug in 2, what I'm going to get is 2 squared plus 6 times 2 plus 5, which is 4 plus 12 plus 5, 17. That's way off the graph. So plugging in 2, I could have done it, but it's not going to help me with the graphing component of it. Okay, what about -1? Let's start with -1 because maybe I should come this way. So -1, we have to be careful. The biggest mistake people make, and I'll show you, is they don't do that correctly. Okay, so if I have -1 squared, that is equal to 1. If I have -1 squared, right, this is 1 squared, which is 1, but then this makes it negative, so it's -1. These are not the same thing, and that is true of any single thing you square. When you're squaring, you always put parentheses, especially if you're plugging into your calculator. If you plug it in like this, you're not going to know, okay? If you do it like this in your calculator, okay, it's not going to give you what you should get. What it's going to give you is -1 instead of 1, -6 plus 5. It's going to give you 0. Okay, but what do we really get? We get -1 squared is 1, plus 6 times -1 is 5. -5 plus 5 is 0. So sorry, this one will give you the 0. Okay, in this case, you get -1 minus 6 plus 5. So it's -7 plus 5, which is -2. Okay, so there we go. That is the difference here. If you plug it in like this in your calculator, it's going to go, okay, 1 squared is 1, make it a negative, so it's -1, plus this is -6, so it's -7, plus 5 is -2. You get 2 very different answers. Okay, so when you're plugging in, you always put parentheses around the number you're going to plug in. I hope that wasn't confusing. I know I took a little time to make an aside there, but I'm saying one person in every class, okay, is going to be the person who does this, who doesn't do it like this, who does it like this. Okay, please don't let that be you, because you don't want that to be you. But this is the reality. If you are not careful plugging stuff in, okay, you're going to get the wrong answer, and you're not going to know until the graph is wrong. That's why we take the time to do this. Okay, negative 2. So negative 2, I'm going to do negative 2 squared plus 6 times negative 2 plus 5. So that's 4. Negative 2 times negative 2 is 4. So this is negative 12. So 4 minus 12 is negative 8 plus 5 is 3. And it actually should be negative 3 because it's 4 minus 12, so it's negative 8. Okay, so now I'm going to go negative 2, 1, 2, 3. So we can see it's going down. I haven't really hit a lowest point yet, so let's plug in negative 3. Okay, I plug in negative 3. I get negative 3 squared plus 6 times negative 3 plus 5. Okay, notice how I'm always doing the 5 because that's a constant term. I'm always adding 5 no matter what. So this is 9 minus, this is negative 18. So 9 minus 18 is negative 9 plus 5 is negative 4. 3, 1, 2, 3, 4. Okay. Interesting. Let's move that down there. Alrighty. So I really have not had a resolution yet, but let's keep going in the direction we're going. Another thing with graphing is you don't want to say, I'm going to shoot down to negative 6, negative 8. Because if you keep getting points, like you're going along a trend right now. If you start going over here, this is not going to help you figure out necessarily what's going on over there. It's not like a line, okay? So that's the other mistake people make is they treat them too much like lines. You have to be willing to put in the time, and if you're not willing, we have to discover a better way to do this. Okay, so this is 16 minus 24, that's negative 8, just like how this was negative 8, plus 5 is negative 3. So, we start to see a repeat here. Okay, see what happens. So what do you think is going to happen when I plug in negative 5? Which one of these other numbers is going to have the same y as negative 5? What do you think? Okay, let's see if you were right. So I'm going to plug in negative 5, so it's negative 5 squared plus 6 times negative 5 plus 5. Okay, and so that is going to be 25 minus 30, that's negative 5, plus 5 is 0. Okay, and chances are when I plug in negative 6, I'll also get 5. And I know that's true because this will be 36. This will be 6 times negative 6, that's negative 36. So I'll have 36 minus 36 is 0, plus 5 is 5. Okay, so here's our parabola. Here it is. Okay, and now it's not as good of a U shape as I could have done on paper, but let's take a look. 1, we have our vertex, our lowest point. It is at negative 3, negative 4. Okay, we have our nice symmetry right down the middle. So we have these are both, so this is negative 4 and this is negative 2. Notice how those are both 1 away from 3. They have the same y, or rather negative 3. Okay, negative 1 and 5, those are both 2 away from negative 3. They have the same y. Okay, 6, negative 6 and 0, those are both 3 away from negative 3. They're the same x distance away, so they have the same y. Okay, and then finally the same thing. So we have this notion of absolute value, right? If two numbers are the same absolute distance from negative 3, because that's the x of the vertex, they're always going to have the same y. Why is this going to be helpful? Well, think about it. If we can find the vertex, right, then once we have a point on one side, we get a free point on the other side. Okay, for example, if I know this is the vertex, negative 3 is the x, that already will tell me that these two have the same y, these two have the same y, these two, so etc. So once I can figure out this x, I get to automatically put this one on. Once I figure out this x, I get to automatically put this one on, and so forth. So if I don't want to plug in negative 6, I don't have to. I plug in 0, and I know that because the x of the vertex is negative 3, and negative 6 is the same distance away from negative 3 as 0 is, they automatically, because it's a quadratic, are going to have the same y due to the symmetry. So that's something that's very unique about a quadratic that makes it really, really cool and sets it apart from some of the stuff we've learned before. Okay, so I know this was definitely a long explanation about this, and that was kind of intentional to break down some of the ideas. Please make sure you, if you need to, pause, rewind, and make sure you understand everything we did in that breakdown. Okay, because in a moment I will move on to the next function. Okay, so now what I have is x squared minus x minus 6. I need to graph this, okay? So think about what we just did, and if you need to, right, I'll set up the table. I'm going to do this one in red. I'll set up the table. Go ahead and try to graph this, okay? So let's think about this one. We'll try this one together, all right? So think back, though. What was the first point that I just went in and put that in there? That is the y-intercept, 0, -6. Okay, 1, 2, 3, 4, 5, 6. I'll talk a little bit more about intercepts on this one. I didn't mention that on the last one, so I'll talk a little bit more about this on this one. Okay? All right, what do I try now? What's another easy number to plug in? The next easiest. It would be, I would try 1. Okay, so I've got 1 squared is 1, minus 1 is 0, minus 6 is -6. Ah, that's interesting. Right? But notice the ones cancel each other out. Huh. That's weird. All right. That's interesting. So, what I want you to do is think about this. Do you know where the vertex is at yet? Do you know what the x of the vertex is? If you think you know it, like write it down or something, and we'll see if you're right in the end. I don't know what's going to go on here. Huh. All right. Well, what should we plug in next? This was not what I expected at all. Wow. What should we plug in next? You know, let's go crazy. Let's plug in 2. So 2 squared is 2. 2 minus 4 is 2. Or rather, 4 minus 2 is 2. 2 minus 6 is -4. So 2, 1, 2, 3, 4. Okay. What about 3? 3 squared is 9. 9 minus 3 is 6. 6 minus 6 is 0. Okay. All right. So we have 0. Now I'll plug in 4. 4 squared is 16. 16 minus 4 is 12. 12 minus 6 is 6. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. All right. What do we have now? What about, so if you were to guess, based on what you see, do you think 5 will be on or off the graph? It'll actually be, to be honest, it'll be off the graph. If you guessed that, good job. We'll have 25 minus 5 is 20, minus 6 is 14. That's way off the graph. I'm not even going to try to graph that one. So now I go to my -1. Okay, -1 squared is 1 minus -1. It's like adding 1, so it's 2. And 2 minus 6 is -4. Okay? Interesting. Now, I have -2. -2 squared is 4. Minus -2 is 6. Minus 6 is 0. Now I've got -3. -3 squared is 9. 9 minus negative 3 is 12. 12 minus 6 is 6. So basically, as long as what comes out of here is equal, that will make sure the respective outputs are equal. All right, so in other words, when I plug in negative 3 and I plug in 4, what comes out of this is the same thing, right? This will be 9, 12. This will be 12, and this will be 9 plus 3, and this will be 16 minus 6, okay? And in either, or rather, minus 4, okay? And 16 minus 4 is 12, and 9 plus 3 is 12, okay? So this is all of the graph that we can really capture. But here's the thing. Where's the vertex? So notice the equal points. Where does it come down to? If you guessed 1/2 was the vertex, you're actually correct. It is a half. Okay, that's interesting. So when I plug that in, what I get is 1/2 squared, which is a quarter. A quarter minus a half is negative a quarter. Okay, and 6 minus a quarter, or a quarter rather, negative a quarter, minus 6 is negative 6 and a quarter. So something like that. So here's the moral here. Not all quadratics are going to have a whole number vertex, right? We were kind of living in a little bit of luxury when we talked about absolute values, because those are nice whole numbers. It's kind of gone now. So it's another thing we got to take off the training wheels with. All right. So all right. So this is my breakdown of this one. It did, believe it or not, go a little bit faster than the last one. Okay, but the idea is we want to plug in until we get a nice table. Okay, now maybe you're starting to notice, how many points did it take you to figure out that the x of the vertex was a half? Were you able to figure out in time? Some of you might have been able to figure out from the first points. And think about it, right? If these two are equal, the x of the vertex has to be right in between them, right? It goes both ways. If two x's are the same way from the x of the vertex, they'll have the same y. But at the same time, if 2 points have the same y, their x's have to be directly, or rather the x of the vertex has to be directly in the middle of those respective x's, right? So it's two ways, right? Vertex, y same, vertex, okay? So I'm going to go ahead, and again, if you need to pause, feel free to do so. I'm going to go ahead and move on to the next one in just a second. Give it a second if you need to, and then I'll move on. All right, so the next one is, this is interesting. X squared minus 6x. What's missing from here? What's missing is that there's no c. The c value is 0. So that when you plug in our easiest point, and I'm going to actually do this in green. And they're not always going to be f of x, by the way. I just did that for personal preference and ease. Okay, I would expect there to be different letters like y's and z's, and as well as it's not always going to be called f. Okay, so we got 0, 0. What do we plug in next? Why not try 1? Plug in 1. 1 squared is 1. 6 times 1 is 6. 1 minus 6 is negative 5. Might as well plug in 2. 2 squared is 4. 6 times 2 is 12. 4 minus 12, negative 8. Three squared is 9. 6 times 3 is 18. 9 minus 18 is negative 9. So we have 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? You see any patterns so far? Let's see if else we can do. Let's try 4. Okay, 4. 4 squared is 16. 6 times 4 is 24. 16 minus 24 is negative 8. So, aha, we have a repeating. So, what do you think 5 is going to be? 5 should be negative 5. Let's see if that's true. So 5 times 5 is 25. 6 times 5 is 30. 25 minus 30 is negative 5, and it is. Okay? What's the next one going to be? 6. It should be 0, right? 6 squared is 36. 6 times 6 is 36. 36 minus 36 is 0. What about some of the other numbers? So look, I have here 7. I have here negative 1. What do we know about their outputs based on what we've seen so far? What we've seen is that they need to be the same. Now look, negative 1, we know the vertex right now. We can see it. This is the vertex. We notice that, if you think about it, sorry, not 4, negative 8. I apologize. 3, negative 9 is the vertex. I don't know why I saw negative 8. 3, negative 9 is the vertex. My apologies. So look, how far is 6 away from 3? It's 3. How far is 0 away from 3? It's 3, right? So if we think about it, we have negative 1 and 7. How far is negative 1 away from 3? It is 4 away. How far is 7 away from 3? It is 4 away. So therefore, 1, negative 1, and 7, right? Negative 1 and 7 will have the same y values as each other. Now, knowing that, what would you rather plug in? Negative 1 or 7? I would argue 7, potentially because you don't have to work with the negatives, so you don't have that chance of not getting it correct. But negative 1 could do it as well. So for example, this would give you 1. This would give you negative 6. 1 minus negative 6 is 7. This would give you 49. 42. 49 minus 42 is 7. Okay? So the idea is you choose which one you want to plug in. And what you know is, okay, what you know is that they're going to be the same. So for example, once you plug in negative 1 and you get 7, you now know that 7 is 7 because they're the same distance away from the x of the vertex. Okay, extremely important. I'm not going to give you any more patterns, but I do want to note something. These are what we call our x-intercepts. Okay, they're where the graph touches the x-axis. Okay, by the end of this year, we might be able to tell from the equation how many of these there's going to be. Sometimes there's 2, sometimes there's 1, and sometimes there's 0. Okay, so our x-intercepts are 0, 0, and 6, 0. Okay, those are very important. Okay, here we go. So this is how you graph this one. Notice there is another pattern, okay? And I'm not going to tell you right now, but I would say, look at the slope between each of the points. What is it? What do you notice about the slope between this point and this point, this point and this point, this point and this point, this point and this point? What do you notice about the slopes? How could that help you get values, even more values, without ever plugging in really anything above what we have right now? Or how could that help you if I only just knew the vertex? Is there a pattern between that and any of the numbers here? That's stuff we want to think about, because the answer to all of those questions that were yes or no questions, at least, is yes, for sure. Okay, so please go ahead if you need to pause and make sure you understood what we did, and then in a moment I will move on. All right, so now I have negative x squared minus 8x minus 12. Okay, I'm going to do this one in black. Okay, notice the difference here. We have a negative x. So where am I going to start? I should start with 0. Okay, here's the problem. Okay, it's always good to start with it. But 0 is negative 12. So all I know is 0 is down here. Now, should I graph off to the left of it or the right of it? Right? Where's the graph going to be? The answer is, at this point in time, we don't have enough information based on what we've learned to know for sure where it is. Okay? So that's a scenario where it would help us to be able to find where the vertex is, because if we had a formula, and by the way, right, just to quickly go back, this one's vertex, if we saw, was 3, -9, okay? And I think I may have mentioned that, but I just want to note, make sure we have that on the graph as 3, -9. So anyway, we don't know where the vertex is. Okay, it would be helpful, but we don't know. So I'm going to just plug in 1 and see what happens. This is just a case where you don't get a whole lot of information because it's already off the graph, but it's pretty close to being on the graph. Okay, so you got to be careful here, and this is the other mistake people make. Remember PEMDAS. So that is why you always plug in, especially on your calculator, with putting the parentheses around the numbers you're plugging in. So 1 squared is 1. This makes it -1. 8 times 1 is 8. -1 minus 8 is -9. -9 minus 12 is -21. So that's telling us, darn it. Now, some of us might say, you know what? This is really, like, what the heck? All of these numbers are going off. I would actually argue that this is actually a really good thing. And you know why? Because now, what's the next number I would want to plug in? Think about it. Why would and why would I not plug that number in? Think about it. All right. The next number I would want to plug in, if you look back at some of my other tables, is a lot of the times we do 2. But why would I do that? Because I know this is negative, this is more negative, so it's only getting more negative. I'm not even going to waste my time with 2. So why that's cool is that, yes, you spent your time and you didn't get something to graph. But what you got is you got the ability to say, I'm done going that way on the x-axis. I'm going to go the other way, okay? So you have to think of even the stuff that doesn't help you directly helps you in other ways. So you really have to have that persistence, okay? So when I plug in -1, let's see what happens. So -1 squared is 1, -1 times 1, right? 1, this makes it a -1. 8 times -1 is -8. And -1 minus -8 is -1 plus 8, which is 7. Okay? And -7 squared, or rather -7, sorry, so let's do that again. 7 minus 12 is -5. Okay? So again, -1 minus -8 is -1 plus 8, which is 7. 7 minus 12 is -5. Okay. Now, thinking about the patterns we've seen, do you think you could find the vertex now? Here's the reality. Believe it or not, once you really get a sense of some of these patterns and what's going on, you actually do know enough to find the vertex now. You wouldn't think so, but you actually do know enough just by looking at the graph and the table, not even the equation. Okay, that's what's cool about it. So what about this? What about -2? Because it looks like when I go this way, they appear to be on the graph. Okay, so -2. So -2 squared is 4. This makes it a -4. -2 times 8 is -16. So -4 minus -16 is -4 plus 16 is 12. Minus 12 is 0. Look, this is going well. Let's try -3. So this is 9. This makes it a -9. Okay. This is 24, but it becomes a positive. So it's -9 minus -24, okay, which is 15. 15 minus 12 is 3. Do you think you know where the vertex is now? Okay, let's see if you're right. I'm going to plug in -4. -4 squared is 16. This makes it a -16. -4 times 8 is -32. So we have -16 plus 32 gives me 16. Notice the opposite things, -16 and then going from negative 16, 16. There's some patterns there. Okay. So anyway, negative 16 plus 32 is 16, minus 12 is 4. So think about what we've done so far. Again, do you see any patterns that are repeating in the graph or in specifically when we find the vertex? Think about what is the graph, what happens when you're actually going through the motions of plugging it in that tells you it's the vertex. That's another reason why we really want to plug in. Okay, what about negative 5? By the way, before I do it, do you think you know the vertex? Okay, let's see if you're right. So, negative 5 squared is 25. This makes it a negative 25. This is a negative 40. 8 times negative 5. So we have negative 25 minus negative 40. So it's negative 25 plus 40, which is 15, minus 12 is 3. So see our patterns? What is negative 6 going to be? It's going to be 0. And I know that because what I would get is negative 36, okay, plus 48. Negative 36 and 48 is 12. Minus 12 is 0. So I should also get this. And I should get this right here. So what's different about this graph? What's the main difference, folks? The main difference is that it points down. Okay? What of these three values do you think made it point down? Let's take a look. So we have this pointed up, this pointed up, this pointed up. What do they all have in common? What they have in common is their a value. Okay, so this is a negative a value, and when a is less than 0, it's going to point down. Okay, and the reason is because x squared is the biggest, where the most of the value of the function comes from. So watch, if I plug in 10, what do I get? I get 10 squared, and then opposite, which is negative 100, minus 80, but it becomes actually a plus 80, minus 12. Okay, if I plug in 1,000, right? How about 100? I get 1,000, negative 1,000, minus 800, minus, and that's actually 10,000. So this is 10,000 plus 800. This is like, say I'm plugging in negative 10. Okay, notice which one of these is bigger? 1,000 by far. So the reality is the x value, the x squared rather, this is the x value that's playing the largest role in the overall what is coming out of the function. So this is going to control the up and down, and so when it's negative, it points down. When it's positive, it points up. Okay? So please make sure you understood this part of it. I encourage you to rewind if needed, and then in a moment I will move on to the last example. All right, here we go. Now what's different here is that this one is larger. Okay, this one is larger than 1. It's actually equal to 2. So what do I start by plugging in? 0. I get negative 5, because that would be all that's left. What do I plug in now? 1. So I get 2 plus 3 is 5, minus 5 is 0. Wow. Now I get, why not plug in 2? 2 squared is 4. 4 times 2 is 8. Okay, 3 times 2 is 6. So we have 8 plus 6, which is 14. Minus 5 is 9. And now I'm going to go off the grid. So I'm going to do negative 1 and negative 2. So negative 1 squared. Now remember, when you do this, remember PEMDAS, you do not multiply. You do not multiply. You do the squared, and then you multiply, right? Exponents, multiplication. At least one person will not do this. At least one person will say 4. because they'll multiply, they'll get -2, then they'll square it. Those numbers are not the same. Do not do this. Exponent first. So -1 squared is 1. 1 times 2 is 2. So that part of the equation, that part of the output is 2. Now I've got 3 times -1. So I'm minusing 3, minusing 5. So 2, -1, -6. So -1, -6. All right. What about -2? So I've got 4 times, right? Because this is squared, you get 4. 4 times 2, I've got 8. Then this gives me 3 times -2, -6. So I've got 8 minus -6 rather. And 8 minus 6 is 2. And 2 minus 5 is -3. Okay. So I got -2. All right. So let's take a quick look. So I did -1. Yep. Okay. So not easy stuff. Let's see what else I get. So far that's what we have. So we have -3 now. So this becomes 9 times 2 is 18. Okay, this becomes -9 minus 5. So 18 minus 9 is 9. Minus 5 is 4. All right. So where's the vertex? That's the question that I'm asking myself. Where the heck's the vertex? Why are none of these numbers repeating? It's actually not very easy to find the vertex. It's not a whole number. It's not even close. And that's the challenge here. How do we find the vertex? Because all we have right now is some scattered points. Let's say we try to graph this. What do we have? All we have is this. It's not much of a graph. But I'll tell you, the x of the vertex is -3/4. Huh. So the x of this vertex was -3/4. The x of this vertex was -4/4. The x of this vertex was 3 -9. The x of this vertex was 1/2. The x of this vertex was -3. Let's look at the numbers here. How could I get any of these based on the numbers? The A's, the B's, and the C's. That's a good question that we want to ask. So really quick, we're going to figure this out in class. But one thing I'm going to show you is, I'll show you one of the variables that it does not have to do with. And to show you that, I'm going to come to this example right here. And I'm going to do this. I'm going to do x squared plus 6x minus 1. So if I want to do x squared plus 6x minus 1, here's what it's going to look like. It's going to have 0, -1. It's going to have, all right, I'll do this in black so we can see the two different graphs. 0, -1. Okay, 1, 6. So we have this point, Okay, now I'll do -1. So I'll have -1. That'll be 1 minus 6 is -5. Minus 1 is -6. Okay, then I plug in -2. So this is 4. 4 minus 12 is -8. 4 minus 12, right. So 4 minus 12 is -8. Minus 1 is -9. One, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now I plug in -3, and I get 9 minus 18 is -9 plus -9 plus 5. Sorry. 9 minus 18 is -9. Now this is -1, so it's -10. Okay? And now, believe it or not, I've actually hit my vertex. Okay? And we can verify this. If I plug in -1, 2, 3, 4, -4, I get 16 minus 24. That's -8. Minus 1 is -9. So it actually checks out. So observe, the C value changed. I changed it from from +5 to -1. How did that affect the x of the vertex, which is now -3, -10, right? The x of the vertex stays exactly the same. So here's my hint for you. C has no impact. All C does is it takes the standard graph of x squared plus 6x, okay, and it just shifts it up and down. So the C has no value. So what we need to do, and this is what we're going to discover, is what is a rule. It's got to involve A and it's got to have B in the rule, okay, and using these two numbers only once each, you can have a formula that tells you what is the x of the vertex. And if we can figure this out, it's going to make the graph a lot easier, because it's going to be easier once we know the vertex to get the quick one then the other, one then the other. So once we get this as the vertex, we can get one then the other, one then the other, one then the other. And now I'll tell you, only needing 5 points and including the vertex, that's going to be really not that tough to do. You'll have 0 in another, you'll have the vertex, you'll only need to plug in one more easy point and then use the symmetry, okay? So look, thank you for watching this video. I just want to say, like, quadratics is a big investment. You have to be really into it. There's a lot of really cool stuff if you give it the chance, okay? It's not going to be easy, but I will tell you, at some point this year, in a high stakes manner, you are going to have to do this without a calculator, okay? And so this is the only way to do it without a calculator, to set up a table, to plug it in, and to look for patterns. So see if you can find any patterns in this video that will help you, because I can say, once we've discovered these rules and these patterns that are meaningful to you and that you figured out, they're going to last you for a while, and they're going to be very, very useful and make graphing, like they say, light work. Okay, so once again, thank you for watching this video. I hope you found it educational. I really encourage you to leave a like or subscribe, and to subscribe to alerts. But again, just keep it up, right? Stay persistent, keep loving math, okay? And remember, as I always say, you can do it. All right, folks, have a great rest of your day, and don't forget to love math.